Okay, we should be live. Go check out biomedical.com. There's lots of interesting tools. You'll be supporting the project this way. And don't forget to provide your feedback. We're available pretty much on any platform under the world. GitHub, Twitter, Facebook, Reddit, TikTok, blah, blah. Well, I'm mainly active on Patreon, LinkedIn, and YouTube. Obviously, there's a bunch of. This was the last tool that was published on the site as a vision impairment simulator. And yes, just realized that we're missing a lot of vision conditions in here, so we'll probably be getting back to it sometime shortly. Yeah, we have a neural net trainer, a simple example. You can change your training set size, the number of hidden layers, a noise level. Yeah, it's not changing live. This probably can be improved, but yeah, it's changing only when you hit that train neural net button. You can see it's having trouble to converge, and if you reduce the noise level, it should be doing better. Sometimes you need to run it like multiple times because it's non-deterministic. Every time you get different results as opposed to a fuzzy logic system. No, it's converging. I don't know what was up if that doesn't seem to get any lower. So it's saturated at 0.04. So that's pretty good. It can also improve the increase the training size, change the number of epochs and see what difference this make. But yes, remember that it's non-deterministic, so even with the same parameters it will run differently every time. So good luck with neural networks. There's some examples and the description below. Go check it out on biomedical.com. Some article, yeah, someone mentioned this one that I forgot, another use of EEG or modality, or it's not quite relevant, but we might have a separate a blog / tool that actually covers amplitude EEG, which is used quite extensively. I used it before, actually mostly originally used in neonatal recordings, so because the number of electrodes is limited. But yes, you can use it for adult recordings as well. So I might leave that blog as is, and we'll start a new one. Probably not today. What else we've got? So we've got a bunch of old tools here. Go check out the pupil detection, eye detection. I don't know what's up with my hair, but the eye detection actually works. So maybe no darkness threshold. Yeah, you need to adjust your darkness threshold because it will be specific on the eye, and this works better. The default is kind of offset, and yeah, you need to select your, yeah, one eye is working okay, that one is not. So that's interesting. Pretty sure that's not the darkest point. There's something wrong. Looks like an error. It meant to find the darkest point in the region of interest. Just seem to be doing it on, yeah, the threshold is important. So I need to adjust the threshold for it to actually work. So probably suggest putting this this eye is always offset. Anyway, play around with it. Let me know what you think. And how would you improve it? Yeah, the biggest tool of all is this bot that plays an ECG detection game. So we covered this extensively. Go watch previous videos. Let me know what score you reached up to when just doing it yourself, or when using the bot as so instead of a competition, you can turn it into a collaboration. You meant to click on abnormal ECG pattern, so that's normal. I'm not clicking on it. I'm getting the extra points. I missed actually this one. No, yep. Don't know, it keeps scrolling. It's getting faster every 50 points. This was obviously abnormal. The bot is doing well as well. This is another normal I'm not clicking on, so it's a correct rejection. This is a hit because it's an abnormal and I did click on it. The bot did the same. So currently we have the same score. That previous one was missing a downward spike after the R wave, same as here. So far so good, but now it's getting faster. And the bot will eventually be kicking my bottom. Yeah, interestingly, the bot is making decision much faster because it, yeah, clicks. Well, it doesn't click, but you know what I mean. It as soon as the waveform is presented to the robot, it's making the decision straight away, and I have to. My score is lagging behind because I have to actually click on the screen, so that takes some time for a human, not for a robot. Once it becomes faster, well, I'm kind of getting distracted already because I had enough. I'm gonna have my coffee, but the bot doesn't need any breaks. I'm actually leading now because the robot made a miss and a second miss. I was like, what? I have to tune up that algorithm. It's a fuzzy logic. It's actually telling you what it does. It did a false alarm as well. That's really odd. Something was up. And I made the false alarm as well, because essentially false alarm is when I click on a normal ECG waveform. I wasn't paying attention to that one, I just guessed. I think I guessed incorrectly. And I missed one. Missed the one abnormal one that I didn't click on. It's becoming faster. We have about the same score as with the robot. Still able to. So I'm not looking at the bot. So currently I'm not collaborating. I'm just playing against the robot. I'm just looking at the waveform. Obviously I can also be like in a collaboration mode if I actually look at the processing of the, oops. Okay, now it's becoming crazy fast. I just have to look, ooh, missed one. Some of them are harder, some of them are easier. Yeah, okay, now I'm not even able to, yeah, probably need to move my mouse to the most left of the screen. I'm surprised I'm still able to keep up with the robot, because the robot did some mistakes as well. So I don't know if you can hear me pounding the mouse or not, probably not. Some noise cancelling with the microphone. Oops, shouldn't have pressed that. Yeah, so now it's too fast. I'm already tired. The bot keeps going strong. don't even know at what FPS frames per second I'm recording this. It might be not moving smoothly in the video. Oops. Oh, that was a false alarm and misses. I can't keep up. I'm like, I need a rest, like my eyes need a rest, but the bot will keep going. It's currently still doing false alarms and misses. That's because the noise level is kinda, well, it's not zero, it's in the middle of that scale. So if I put it higher, it will start making more mistakes, but then the human might be making more mistakes as well. Yeah, so that's with more noise. This is less noise. With less noise, it should, yeah, it's obviously easier for me. I can actually do some more. But in this condition, the bot will not be making any more false alarms or misses. Then with increased noise, yeah, false alarm, false alarm, false alarm. It's essentially labeling everything as abnormal, which is obviously not good. That's what that noise level slider is for. It's just designed to show you that machine learning algorithms make mistakes when the signal is noisy. That's exactly what it does. The fuzzy logic algorithm, the machine learning, is looking at positive peaks, negative peaks, raw amplitude, R peak amplitude, so the amplitude of that major peak in the ECG, and intervals between P wave, R peak, and T wave. And it has a threshold for each one. So it's a deterministic system. It will give you same result every time. So it's giving you an abnormality score out of this 1, 2, 3, 4, 5, 6 parameters. Fairly straightforward. And yeah, so this is essentially showing how, oh yeah, if we collaborate with the bot and can be just looking at that abnormality score, if it's very high, it means the machine is confident. If it's essentially below 0.5, it means it labels normal. If it's above 0.5, it's labeling abnormal. And the level of that abnormality score, how close it is to 0 or 1, will determine how confident the robot is. So I can use that and we can make decisions together. Yeah, you could see the 0.51, obviously it's sitting on the, you know, on the threshold there. So it's like, it's essentially the robot saying, I'm not quite sure. So if human and robot working together, that's the one you should be paying more attention to. And yeah, that's what the score is doing. The bot already got like 3 times a better performance than myself. It's fairly straightforward. There's only one normal ECG wave and 4 or 5 abnormal type waveforms. So it shouldn't be complicated. Anyone should be able to do this task. What else we've got? So we got something, yeah, this stuff. Yeah, got annoying, making annoying sounds. By the way, I do split the video later. If anything interesting happened, I will be generating standalone videos out of this live stream. To remember to do some sort of, you know, click or something to be able then in the video editing to remove that segment. like if I'm doing blah 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 blah. No, it needs to be something like, you know, like that in the movies. The action, no action. This one is yes, currently it's just a silly game, but potentially could review time series data that way instead of the traditional scrolling on the screen. Could be just looking in one spot instead of, I don't know. And this could be the number of particles, could be the number of channels. Normally we do 20 something in EEG, and the speed could be your frequency. You could also do size changes of each particle that will simulate amplitude of the signal. So it goes, and yeah, the problem with this one, they bounce all over the place. Could be going just clockwise. For reviewing EEG, and then if you have a seizure or something, it will go crazy like this. Let me know what you think and how would you turn it into something more useful. And yeah, go check out the website. And do we have time for development? I don't know. See quickly what we've got. So we're generally doing a couple of things. Should we do a fun one or a more serious one? What do you reckon? We have Game of Life that we are simulating. Get to it in a sec. Just open it so we don't forget it. We also have a cochlea implant simulator. Yeah, that's obviously, as you can tell by the sound of it, it's a more serious business. Have all these prompts for it. So essentially it will be a model of a cochlear implant. It will take the sound of let's quickly start the GPT. You also have so we normally using GPT-4 and GitHub Copilot. We normally just came to a point where so GitHub Copilot is good at that can do a chat. Ask Copilot to explain the project, but we do need to pop it into GPT-4 as well because it's just better. It's just better. We actually, so I want to run everything in JavaScript if possible. Yeah, we don't want this, for example. Structure table, yeah, that's fine. Yeah, we need that. We need the HTML file. HTML file conveniently has this description as well. And primarily want to rely on JavaScript. And this JavaScript is just 100 lines of code, which is okay. We do want to just ask how to change the code because we are lazy. But we'll see in a sec what it does. 1, 2, 1, 2. It doesn't do much at the moment. That's unfortunate.
It looks like you've already set up a basic Flask web application with some JavaScript for audio processing and visualization on the client side. Your current code structure is mostly set, but I can suggest a few improvements and clarifications, especially if you want to enhance the functionality or maintainability of your code.
Yeah, that's
Improved route handling. If you plan to expand the application, it might be a good idea to organize your routes better and maybe even consider using blueprints for scalability. Configuration. It's awfully good practice to separate configuration settings, like debug and port, into a configuration file or environment variables. Responsiveness. Ensure your CSS handles different screen sizes. This might involve using media queries or frameworks like Bootstrap or Tailwind CSS. JavaScript modularization. As your JavaScript grows, instead of splitting it into modules. This helps keep your codebase clean and maintainable. Web Audio API usage. Your current setup for Web Audio API is pretty basic. You might want to explore more features of the API or handle more edge cases, like different user environments. Visualization enhancements. If the visual aspect is crucial, you might consider using a library like D3.js for more dynamic and interactive visualizations. And in a separate file, audio processing. JS, you can define the functions set up audio nodes, connect audio nodes, and visualize. These are just starting points. Depending on your specific needs and future expansions, adjustments will be necessary. Let me know if there's a particular area you'd like to dive deeper into.
I really don't want it to be more complicated than just one file. But we will go with it because obviously the bot knows better. So we generate the audio processing JS. Normally what we do, just pop in and this is in static. So Control I to change that file. What on earth? What are you doing? Just need to do this really. Hey, okay, yeah, we're splitting the thing. So we go with what it says for now. Didn't finish generating that. A bit slow. That's okay, because it does a lot of coding for us. So we shouldn't be complaining.
Certainly. To better structure your JavaScript code, we'll define the setup audio nodes, connect audio nodes, and visualize functions in a separate file called audio processing, JS. This modular approach makes the code easier to manage and test. Here's how you might structure this file. Modularity. Each function handles a specific aspect of the audio processing setup. They're exported so that they can be imported and used in other scripts like your main application script. Global variables. The use of window scope variables, window, filters, window, compressors, etc., allows these structures to be accessible across different modules without passing them explicitly. This is helpful in scenarios where you want to maintain state across different parts of your application, but should be used cautiously to avoid polluting the global namespace. Real-time visualization. The visualize function is designed to continuously update the canvas, providing a real-time view of the audio processing effects. This structure should give you a solid foundation to further expand and refine your audio processing functionalities. If you have specific functionalities or enhancements in mind, feel free to share them, and we can refine the code further. Sure, let's create a well-structured main, JS that ties in with the modular audio processing, JS we discussed earlier. This script will handle initializing your application, managing user interactions, and integrating with the audio processing logic. Module imports. The script imports functions from audio processing, JS, ensuring the setup and visualization logic is maintained separately, enhancing code readability and maintenance. Event listener for DOM content loaded. This ensures that the script executes only after the full HTML document has been completely loaded, avoiding any element targeting issues. Start audio processing function initializes the audio context if it hasn't been created, allowing audio operations to be performed. It checks and resumes the audio context if necessary, addressing an issue where browsers might suspend audio operations to save resources or adhere to user interaction policies. Accesses the microphone using the web APIs and sets up the audio stream as a source for the audio context. Calls the imported functions to set up nodes, connect them, and begin visualization. This separation of concerns keeps your main, JS clean and focused on handling user interactions and high-level application logic. Error handling handles possible errors, such as failure to access the microphone, by logging them to the console. Make sure your HTML file links to this script correctly, and ensure that your server serves the audio processing, JS as a module for testing locally, as ES6 modules are subject to course policies. Typically, your less than script greater than tag in the HTML would look like this.
One. It's still not doing anything.
This structure should provide a clear and maintainable way to handle your application's main logic. If there are specific functionalities or integration details you need to address, feel free to mention them.
So a good thing is that we can do this. be a processing sound. The green bars are not moving. I suspect we're not actually processing the audio from the microphone. Hey, how to change the code? Yep. Yep, doing some logging. The visualize function would be why is visualize also in the audio processing? Doesn't make much sense.
The issue you're experiencing with the static green bars in your visualization likely stems from the way the audio processing chain is set up or how the visualization function is interacting with the audio data. Since the bars are not moving, it can indicate that either the audio data isn't being processed correctly or the visualization logic isn't updating based on the audio data. Check audio node connections. Ensure that all audio nodes are properly connected in sequence and that audio data flows through this chain. Sometimes a misconnection can hold the audio processing. Verify data flow. Insert console.log statements at different points in your audio processing chain to verify the data is flowing and nodes are processing the data as expected. Update visualization logic. The current visualization might not be effectively capturing changes in audio data. Let's add some debug outputs to see if data is being updated and then ensure the visual representation matches the audio data processing. Here's a refined approach to debugging and improving your code. Enhance visualization function. Add more diagnostic logs to understand what's happening with the audio data. Ensure that each filter is properly connected not just to the next filter, but also to an output node. Run your application with these modifications and observe the console outputs. The logs will help determine if the activities, filter activity and envelope activity, are changing as expected when audio is processed. This approach will help pinpoint whether the issue lies in the audio processing setup or the visualization logic. If the activities logged are static or zero, there may be an issue with how the audio is being captured or processed. If they're changing but not reflecting visually, the issue might lie in how the canvas is being updated.
Normally I don't like Copilot's suggestions. Oh, come on. Might go a bit in. I think something is missing. We have the following error. The code that we currently have is above. Can you generate a response of how to update the code exactly so this error goes away and any other issues with the code are fixed? Yep.
The error message you're encountering, failed to execute, connect, on, audio node, input index, 0, exceeds number of inputs, 0, indicates an issue with how the audio nodes are being connected. This typically means that you're trying to connect an audio node in a way that isn't supported by its configuration. Correcting the audio node connection issue. Correct audio source connection. Your current code mistakenly tries to connect the first filter to the audio source incorrectly. You need to ensure the audio source connects the first filter properly. Ensure proper sequencing. Check that each filter and compressor chain is properly sequenced. The error can occur if there's a confusion in connecting the filters, compressors, and envelope followers. Here's how you should update your connect audio nodes function to avoid this error.
One. Well, something's moving there, just being saturated. Yeah, it's moving there as well. So it's just too much like noise in there.
Additional recommendations. Audio processing visualization update. Make sure the visualization function uses real-time data properly. The visualize function should continuously update based on the data from the analyzer nodes. Debugging and validation. Use console.log statements or debugger tools to trace and ensure all nodes are properly processing data. For example, check for queue data and time data right after fetching them to ensure they contain expected values. Here's an updated snippet for the visualization to make sure it dynamically updates based on the incoming audio data. Try implementing these changes and see if the error resolves and your visualization starts to reflect the audio processing dynamically.
1 1 1 1 1 1. 1 1 1 1. Okay, this visualization function seemed to work okay. That's what I previously had. The green bars are actually changing. The filter activity is jumping around. But we need to improve the visualization because it's not actually changing much. Can you explain what being visualized and how to improve it? Can you check the visualization? It's seem to be being saturated at the top of the canvas, so I don't see the changes clearly. Can you also explain what the visualization does? We might need to improve it so that the dynamic range is better. In other words, change the sensitivity of the chart. Yep. One more. One more. It's gonna crash on me.
From the description of your issue and the visible saturation of the bar heights at the top of the canvas in your visualization, it sounds like the dynamic range of the visual representation needs adjustment to more clearly show the variations in audio signal processing. This adjustment will help to ensure the changes in the audio input are more distinct and easier to interpret visually. Your current visualization works by creating two sets of bars for each frequency band. Filter activity. This shows the average magnitude of frequencies within the band after passing through a bandpass filter. Envelope activity. This represents the output from the envelope follower, which tracks the amplitude changes of the filtered signal, providing a smooth representation of its energy. Issues and improvements. Scaling issue. The saturation at the top suggests that the values might need scaling to fit better within the canvas height. Dynamic range adjustment. Adjusting the sensitivity so that smaller changes are more visible, which might involve applying a nonlinear scaling function to the values.
One. Yeah, so again, it's actually a noise in the lower frequencies.
Let's implement these changes with a logarithmic scaling approach to enhance the visibility of smaller variations. Logarithmic scaling, using math. Log 10 helps in expanding the dynamic range of quieter sounds while compressing the louder ones, making the visualization more sensitive to changes in quieter sounds.
Yeah, so that's
This method is commonly used in audio meters to better reflect human perception of loudness. Visualization adjustment. The scaled filter activity and scaled envelope activity calculations include a small constant, 1, to prevent taking a logarithm of 0, which is undefined. What to expect? This update should make the visual representation of both filter and envelope activities less prone to clipping at the top of the canvas, making it easier to observe subtle changes in the processed audio data. This should give you a clearer, more detailed view of how different audio inputs affect the visual output, especially for signals with low amplitude.
How many bands do we currently have? Might be a good question for Copilot. As you can see from the image, I do get the red bar fluctuating very slightly, and the green bars seem to be saturated in the middle of the screen. How do we fix this? So it said that the number of bands is determined by the length of the frequencies array. There are 10 frequencies specified. I think these frequencies might be needed in tuning. tuning up. Yep.
Based on your setup and the screenshot provided, it appears you have 10 bands, as dictated by the length of the frequencies array in your audio processing JS script. This array defines specific frequencies at which bandpass filters are applied, thus creating 10 distinct frequency bands.
They're meant to be changing over time.
If the green bars are saturating the middle of the screen while the red bars are fluctuating slightly, there are a few steps you can take to optimize and potentially fix these issues.
Oops. I want to comment that.
If the bars are saturating, it might be beneficial to adjust the scaling function used in your visualization code. As I previously suggested, a logarithmic scale can help, but you might need to fine-tune the scaling factor.
1, 1, 1, 1, 1, 1, 1. Oh. That was a bit better, but I still don't get it.
If you believe the chosen frequencies might need tuning, consider the characteristics of human hearing or the specific requirements of your simulation. Humans typically hear between 20 Hz and 20 kHz, but for educational purposes, you might want to cover a range that showcases different aspects of hearing. Low frequencies, important for understanding bass sounds, e.g., 20 Hz, 50 Hz, 100 Hz. Mid frequencies, often crucial for speech recognition, e.g., 500 Hz, 1 kHz, 2 kHz. High frequencies, relevant for high-pitched sounds, e.g., 4 kHz, 8 kHz, 16 kHz. Here's an example of how you might redefine your frequencies array to cover a broader range.
No, I don't want to cover broader range. I want to cover the range of my microphone. Don't I need... It seems to be outside the range of my microphone.
The analyzer node settings in your audio context, such as FFT size and the range of frequencies it analyzes, could also impact how the data is visualized. Increasing the FFT size can provide more detailed data.
One, 1.
Ensure that each node is correctly connected and that there are no issues in the signal chain which could cause unexpected saturation or clipping. Here's how you can adjust your visualization function to apply these updates. These adjustments will help improve the dynamic range and visibility of the visualization, better representing the actual audio processing taking place.
2, 1, 2, 1, 2. Is this better? Not sure. Might be slightly better, but I don't quite understand. What? Can you explain the visualization again? First, it seemed to be not sensitive enough. Second, we want to improve it. Why do I only see So most of the changes in the lower frequency range, does it mean that my microphone, there's a limitation of my microphone? The green bars are not changing, and I don't essentially see any change in the higher frequencies. I think it's a limitation of my microphone. How can I improve the code? Yep. Yeah, when it's generating slowly like that, it means I have to give it a rest. I think that's when we also about to hit the limit. But sure, that sentence changed. Clear.
It seems like you're encountering a couple of issues with the sensitivity and range of your visualizations, especially concerning how they respond to different frequency bands. Let's break down the concerns and address them. Visualization mechanism, frequency data, filter activity. This is measured using the analyzer node, which provides a frequency analysis across the defined bands. Each bar represents the average amplitude within a specific frequency band after the signal has passed through a bandpass filter and a compressor. Time domain data, envelope activity. This tracks the envelope, outline or shape, of the audio signal across time, smoothed out by a low-pass filter. It provides a visual representation of how loud or soft the sound is across time, irrespective of its frequency content. Sensitivity issues. Initially, your visualization may have seemed insensitive because of the linear scale used to display amplitude changes. By switching to a logarithmic scale, as you have done, you can better capture the subtleties and nuances in amplitude, which is more aligned with human perception of loudness. Microphone limitations. If changes are mostly seen in lower frequencies and not in higher frequencies, they might indeed point to microphone limitations. Many standard microphones, especially those built into devices, have a limited frequency response, often biased towards mid-range frequencies suited for voice. High frequencies might be attenuated both by the microphone's physical capabilities and by environmental factors, e.g., room acoustics.
One, two, 1, 2. This is not much better, is it? It's going all the way to 5,000. I thought it will have to be reduced. One, two, 1, 2, 1, 2. One, two, 1, 2, 1, 2. Yeah, one is just being saturated.
Improving code for better visualization and testing, given the potential limitations of your microphone and to improve visualization. Test with known sound samples. Use audio files that cover a broad frequency range to test your application. This can help determine if the issue is with the microphone or your code. Adjust analyzer settings. Increase the FFT size for more detailed data and possibly adjust the smoothing time constant to make the visualization more responsive to changes. Modify frequency bands. Adjust the frequency bands to ensure they are within the detectable range of your microphone. If your mic is weak in high frequencies, focus on lower to mid-range frequencies for clearer results.
Yeah, using decibel as scale makes a lot of sense. So that's the filter activity. What's the green one again? Oops. One, two, 1, 2, 1, 2. 1, 2, 1, 2, 1, 2.
Further refine the logarithmic scaling or consider a different approach like dynamic range compression, which compresses the scale of inputs to a narrower, more manageable range of outputs. Debugging. Add more detailed logging to understand how data varies across different frequencies. This can help you pinpoint if certain frequencies are not being captured well or if the visualization isn't accurately representing received data. By implementing these changes and testing with known sound samples, you can better assess whether the issues are due to the code, the visualization scale, or indeed limitations of your hardware. This approach also gives you a more robust testing framework to ensure your simulation behaves as expected across different use cases.
What's the green one again? Just sitting there doing nothing at all. Okay, don't I need to reduce the frequency range to be suitable for a standard microphone? Also, what's the green bar doing again? It seems to be not changing at all, just sitting there. And I can see only limited variance in the red bar. Can you explain the difference and suggest code improvements? One, two, one, two. One, two, one, two, one, two, one, one. One, two, one, two. One, two, one, two, one, two. So it seems like maybe it's using the wrong microphone setting.
The issues you're observing with the green and red bars can be addressed by understanding the role of each bar in the visualization and adjusting your audio processing and visualization code accordingly. These bars represent the average magnitude of the frequencies within each band after the audio has passed through a bandpass filter. This is calculated using the getByte frequency data method of the analyzer node, which provides a snapshot of the current frequency data.
Okay, that makes sense.
These bars visualize the envelope, or the smooth outline of how loud the audio signal is over time within each frequency band. This uses the getByte time domain data method to measure the waveform's amplitude over time, smoothed by an envelope follow circuit that includes a rectifier and a low-pass filter. If the green bars are static, they might indicate that the envelope follower isn't capturing changes effectively, or the settings might not be optimized for the types of sounds being analyzed. Potential issues and solutions. Frequency range limitation. You've noted the need to reduce the frequency range to match a standard microphone. Typical inexpensive microphones might have a frequency response from about 100 Hz to 15 kHz, but can be less sensitive at the extremes. Adjusting your filters to focus on this range might yield better results. Static green bars. If the green bars are static, it suggests that either the amplitude variations within each frequency band are very minimal or the envelope follow settings are not sensitive enough to detect these variations. Limited variance in red bars. Limited changes in the red bars suggest that either the audio input doesn't contain significant components in the frequencies being monitored or the scale of visualization isn't sensitive enough. Code improvements. Adjust your frequencies to better match the expected input from a standard microphone. Adjust the envelope follow settings to be more responsive.
One, two, one, two, one.
You might need to tweak the curve
One,
or the
two.
frequency of the low-pass filter.
One, 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 two. 1, 2, 1, 2, 1, 2. 1, 2, 1, 2, 1, 2, 1, 2.
Consider adjusting the scaling further or implementing a dynamic compression to handle a wider range of signal amplitudes.
One, two, 1, 2, 1, 1, 2, 1. Yes, you can hear the noise in there. And the envelope is still not doing much. What? What? That filter is funny. Filter meant to make it flat, flat, flat. It's not. It's barely changing. Is that? One, two, 1, 2, 1, 2. The envelope is funny.
Add console logs to inspect the actual values being processed and visualized.
We currently have anything in the console? No, it's be useful to. One, two, 1, 2. Okay. 1, 2, 1, 2. That line of code is it? Field activity and envelope activity, so it should go over here. No. No idea. 1, 2, 1, 2, 1, 2. Well, at least it's doing something now. Okay, I have to finish up. Go check biomedical.com. Let me know what you think. You'll be supporting the project that way. That will be great help. And we'll see how we go with this tool.
Here is how you might modify your visualize function to reflect these changes and help diagnose issues.